One of the reasons that we want to investigate summations at this point in the course is because it gives us a useful way to be able to write a sum of approximating rectangles to find areas. I want to show you how to do this in one very specific instance. This is where we're going to choose the right endpoint approximation. In other words, instead of choosing the highest or lowest value in a subinterval, we're just going to choose the right endpoint. And I want to show you how it gives rise to a very convenient way to use summations. So let's suppose that we just have some arbitrary function, which I'll just call y equals f of x. We don't know what it is. We just know it's a function, and we want to find its approximate area on the interval AB using n subintervals. We don't know how many subintervals there are. Well, the thing to observe here is that, first of all, the length of each subinterval is going to be the length of the total interval divided by n. So we know the length of the interval a minus b has a length of b minus a. That's just how you would do that. You take b, you subtract a, you get the distance between b and a. So if I take that distance and divide it by n, I get that each subinterval is going to have a length of b minus a over n. If I'm using the right endpoint approximation, and that means I've just drawn it here with 3 subintervals, even though I really intend for there to be n of them, I'm going to use these points. These are the ones that I'm going to plug in. These are the values that I'm going to plug into. I'm going to plug into the function f to get the heights of these red dots here. And that's going to give me, of course, the rectangles like that. That gives me that rectangle, and that rectangle. So here, I'll just write out a few of them. Right, subinterval 1 and 2. Actually, let's do 1 first. The first subinterval, its right endpoint is going to be the width of the subinterval further to the right than a. So that means that its right endpoint is going to be a plus the width of the subinterval, which is b minus a over n. Now, for subinterval number 2, that's the one over here, that's going to be a plus, I've got 2 subinterval widths, so that's going to be 2 times b minus a over n. And you can see that if I had a third subinterval, I do, but it's the last one, so I don't really want to write that. The point is that every time I move to the next subinterval, I simply take a and add that number of subintervals times the width of the subinterval. So the nth subinterval is going to have a right endpoint of a plus n times b minus a over n. And yes, I know that simplifies to b minus a. This whole expression simplifies to just b. I know that, but I want to write it this way just to demonstrate to you that what I'm doing is to get the right endpoint, I take a and then add however many multiples I need of the width of the subinterval. What that means is that I can actually write out the area of each rectangle this way. The first rectangle is going to have an area of f of its right endpoint, so that's f of a plus b minus a over n. Where did I get that from? That's the right endpoint. I'm plugging it into that point, into f, in order to get the height of the rectangle at that red dot. So the height of the rectangle is that, and then times its width, which is b minus a over n. The second rectangle is, I'm going to plug in this point, which is a plus 2 times b minus a over n. So I plug that into f. That's a plus 2 times b minus a over n, then times the width of the rectangle, which is b minus a over n. So here I have the width and the height. Here's the height, and here's the width. And then finally, you can just see hopefully you can see what the pattern is here, since we've already covered how you find the right endpoint. That means the area of the nth rectangle is f of a plus n times b minus a over n times b minus a over n. Well, remember what we do to find the approximate area is we add up all the rectangles. So that means that the area is approximately equal to f of a plus 1 times b minus a over n times b minus a over n plus f of a plus 2 times b minus a over n times b minus a over n plus dot 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 f of a plus n times b minus a over n times b minus a over n. Well, this is really a summation because if you look at what keeps increasing here, it's just going to be this. That's 1, that's 2, and it goes all the way up to n. So it's like this is the k equals 1 term, this is the k equals 2 term, this is the k equals n term. So I can write this in this form using summation notation. I'm just going to say the sum from k equals 1 to n of f of a plus k times b minus a over n times b minus a over n, where this is the width of each rectangle and this is the height of each rectangle. So this is an important formula because this gives us a general way to write the right endpoint approximation of the area under an arbitrary function f using an arbitrary number n of rectangles.